were for living environment class. So students would be in 9th grade in my school. Some other schools do it in 10th, but usually it's either 9th or 10th grade students. And it's a part of the heredity unit. So students in the lab are going to be using model organisms or dragons, and they're going to create chromosomes, cross their dragons, to observe the genotypic and phenotypic outcomes of their crosses. So it's really important that I stress to them that they're modeling the work of scientists before them, like Gregor Mendel. He used peas as a model organism, so they would be using a model organism just like real scientists. This would take place probably on the second day of the unit, and students would already be introduced to key genetic terms like allele, genotype, phenotype, things like that, and they would already have completed molecular genetics and sexual reproduction.
Theme, and she's getting the students thinking, but a problem with chemistry is people tend to not see where it is. And when you get into applications of chemistry, then people start to realize it isn't as much a foreign language, it's right around them. So very nice job. Any questions for Laura before she leaves us? Okay, Laura, I think you've answered all their questions. We'll be doing more interacting online too. Very nice. Let's see, Andrea, I think we've got you. I don't know if I said that right. We could get you up next. And I'll turn my mic off on, and if it goes much more than 4 minutes, at about 4 minutes, I'll make some kind of a gesture to let you know to start wrapping up, and I think we're doing a pretty good job of staying about on time. So I will turn my mic off, and it's all yours, Andrea.
Can everybody hear me okay? Great. So the lessons that I developed were for living environment class. So students would be in 9th grade in my school. Some other schools do it in 10th, but usually it's either 9th or 10th grade students. And it's a part of the heredity unit. So students in the lab are going to be using model organisms or dragons, and they're going to create chromosomes, cross their dragons, to observe the genotypic and phenotypic outcomes of their crosses. So it's really important that I stress to them that they're modeling the work of scientists before them, like Gregor Mendel. He used peas as a model organism, so they would be using a model organism just like real scientists. This would take place probably on the second day of the unit, and students would already be introduced to key genetic terms like allele, genotype, phenotype, things like that, and they would already have completed molecular genetics and sexual reproduction with the key events of meiosis, the concept of a gene, things like that. And throughout the lab, the point is for them to discover or model key genetic principles like segregation of alleles, independent assortment, and genetic linkage. Next slide, please. Great, so this lab will be engaging to students mostly because it's using mythical creatures that young students are really interested in. Many different cultures have dragons as a part of their myths, and if not, they've probably seen a movie where dragons have been a part of it. Of course, I'll also have pictures available for students who might be unfamiliar with dragons so that they can still participate in the lab. And what's great about this is it's pretty flexible. You could use any mythical creature like a Pegasus, a gargoyle, a unicorn. So you can sort of go off of what your class is interested in. Another reason is that they sort of have ownership over the traits that they're studying. They're going to decide what traits in dragons they want to study as a class. For example, they'll pick, we want to study the fire-breathing trait, or we want to study the wing trait. We want to study the skin color trait. And then they'll actually go and map the genome of the dragon using a model. So then they'll be able to test their own hypotheses which they will create based on the genome of the dragon. So they'll say, we want to see if all dragons that have pink skin are also fire breathers, or something like this. That will make them care more about the outcome. And then lastly, it's really important, like I said before, to connect it back to the work of real scientists so they don't think that it's silly. Sometimes, if you're working with models like popsicle sticks, they might not think that it's that important, but you need to combat that by saying that scientists use models on an everyday basis. So Gregor Mendel used pea plants not because he necessarily wanted to, but because they were readily available and cheap. And fruit flies are used as a model organism, not because they're particularly interesting, but they're easy to work with and serve for models for other organisms. All right, next slide. And the data that they're going to collect will be their own data. So they will generate that through their crosses. They will actually model what happens in meiosis with their chromosomes, and then they will count out the genotypes and phenotypes that result from the crosses. They choose to use Punnett squares to compare the actual results of their crosses with the probability that those results would happen, and we'll analyze them using either graphs or statistics, depending on what's more appropriate. And we'll also then aggregate the class data so that we can look for bigger trends like linkage or independent assortment. Those are things that we would see on the class scale. And that's about it.
Really very nice, Andrea. Can you tell me, I think you had a link on your first slide, and I'll pass these out. Is this something students can go to on their own too when they're not in the class?
As far as the actual lab itself, like can they access the lab?
Yeah, can they go and make crosses on their own? I know there's some software that will let you go back in and if they wanted to do extra work outside of the class.
Yeah, I haven't looked into that. The models we would be using would actually be physical models, so hands-on manipulatives, meaning probably popsicle sticks. Of course, they could take those home, but I'd be really interested to learn about software that you were talking about. Maybe if you could send me the link in an email. That link was just for the picture.
Oh, okay. Actually, I thought you had found some software there. Now, I know they do have software. There are a number of vendors coming up with it, and I think even some for free. So I see you were one step more imaginative. No, that's great. And maybe that's some software you could make someday. I think teachers would love to send kids there. They're in those fantasy worlds. Yeah.
I mean, that would be really cool as an extension activity. I think sometimes, at least starting off, I like to have them sort of work with their hands to sort of get the down and dirty so they can actually mimic meiosis to show that they're understanding it, rather than having a software program sort all those things out with them and only see the results. Like that way they have to decide how they're going to mimic the alleles actually separating during meiosis, whereas on a software they would have to, that would already be done for them. So I think there's that benefit, but as an extension, I think that would be really cool.
Oh, that's good. So you could kind of pace it and maybe have some of the others for extra credit after you're comfortable with their getting the basics.
Great.
Yeah, well, that's a great idea. And I like your point about models. They aren't just for play. And Gregor Mendel, didn't pick pea plants because that was the only thing he cared about. We have to go pragmatically with what we can use. So that's, Andrea isn't in the voting sheet. Thank you. You know what? Maybe tonight before you vote, I will go back in and be sure that I've got everybody's name in there. Andrea's last name is Covey. So I hope I got that in. Does anyone see her there? Okay, I will go back in and correct that.
I'm in the comments part, but I didn't have a number, voting part. So.
No, that was my mistake. I apologize. And Jason came in a little late too, so I'll see if I can get everybody there. The voting doesn't go away, I think, even if I add another line, but I'll figure that out and correct it. Very nice job, so thank you very much. I appreciate that. And I guess we're about ready to go to our next person, Rich. If you want to come on stage, and thank you very much, Andrea.
Okay, can everybody hear me? Okay. So this lab that I'm going to be doing with my students involves analyzing the angles of the sun for different locations on Earth. This is kind of a hard concept for students to get. As you see from the Earth here, and the arrows pointing at each location, just the fact that Earth is round will give you different angles of the sun actually hitting the surface of the Earth. And the fact that it's tilted 23.5 degrees relative to the plane of the sun makes that concept even more difficult. So I want to kind of drive these concepts home. I'm going to be guiding the students to collect data from different locations on Earth, and then they're going to put that into a spreadsheet, which they're going to develop themselves, and then we're going to answer some questions. This is kind of a problem-solving lab or a learning segment. So we can go to the next slide. Okay, so data is going to be collected from 5 locations on Earth. I'm going to give them 4 of those because they're important as far as seasons are concerned. Then I'm going to let them choose a 5th location. I'm going to try to guide them into the direction of choosing a location at a higher latitude, either north or south, it doesn't matter. So they're going to get the latitude and longitude for both those locations. They're going to get some information as far as the angle of elevation for each location at 4 different times of the year. So those are going to be the vernal and autumnal equinoxes, and then the solstices for both summer and winter. And also the clock time at solar noon. Solar noon is when the sun is due south from a given location. And there's actually a cool website where they're going to go to where they enter in the location of each city, and all this information pops up. All they do is change the date. And so what I'm going to have them do is pair up. One of them is going to actually be putting in the data, while the other one is filling in the spreadsheets with the results. And then the real kind of meat of this comes in answering the questions. And let's see, 1 second here. So I actually give them a question about calculating how fast the Earth is rotating due to the clock time at solar noon, and there's a way they can do that. It just kind of takes a little time, but it's giving them an opportunity to get real world data and use that to solve real problems. But my favorite task that I have them do is I have them actually construct a house, draw out a house, a diagram that uses passive solar heating, and they're going to take the information from this data set, and they're going to make a diagram of a house that is most efficient. So these windows are going to face the sun, and the angle of the roof is going to help out as far as heating and cooling the house at different times of year. So the real goal here is to get them thinking about real world applications as far as the data they're pulling from this website, and thinking about how seasonal variation, the causes of those for different locations on Earth. So that's pretty much it. Does anybody have any questions?
I think once again, you've left people speechless. I like the way you're going to give them an actual application where the amount of solar energy will make a difference. And going to those different cities, I think will pique their interest many ways. So I think that's should be a really engaging exercise, and I think always the test will be if they go back and do more work on their own. So hopefully they'll go back and check other locations. Very nice, Rick. I appreciate that, and I think our